in that case, one of the first things that you need to decide upon is the message queue / the message broker that you want to bring into your project. So what are the tools out there that you can look into? What are the things that you might learn during that journey? What are the conclusions that you might have? And what are the questions that you can ask yourself? I am Poornima Nayar. I'm one of the software engineers and solutions architect at Particular Software, where we build End Service Bus and the entire platform around End Service Bus. And I will be talking to you about all these questions that I just asked you or posted to you today. I have traveled from United Kingdom to be here with you all today. So I was at NDC Melbourne. So some of you might have seen me at NDC Melbourne last week. And today I'm at Sydney, presenting from the Sydney.NET user group. And Poornima Nayar is my LinkedIn /X /Blue Sky handle. So feel free to reach out to me if you have any questions. Or if you are in my in-person audience today, I am here to answer any of the questions that you might have after the session. And non-work me, I live with my husband and my nearly 11-year-old daughter in Berkshire, which is outside London. I read a lot, and I am also a student of Carnatic music vocals, which is a stream of Indian classical music. Thank you to the wonderful organizers, but there is an app which you can scan and collect SSW points with. And if you have any feedback for my session today, please again scan the QR code on the screen and give us some feedback, because speakers can only go so far. We need the feedback to grow and continue presenting. Back into the session, one of the questions that you might get asked, say by one of your team members in the project, or say you have another project team working on another project, they might ask you, why not HTTP? You have been using HTTP, gRPC, or HTTP APIs, or GraphQL so far, but why are you now doing a 180-degree turn and going into messaging? The short answer is temporal coupling. Yeah, this is what you want to avoid in a high-performant, high-throughput system, and this is where messaging comes in and helps you. So what is temporal coupling? Imagine the old school phone conversations where I had to dial to reach out to my friend and talk to her. She might be available to talk, in which case I get a response. If not, the fact that I even called her has just evaporated into the thin air. So both parties need to be up and available at the same time. So we are reliant on the HTTP toolkit of request response, and that is what the HTTP-based APIs are all about. Now, imagine a distributed system built using this kind of HTTP request response-based services. You might have 10 services, and one goes failing, then you have a cascading failure. Everything falls flat on the face of the user. Not only that, you have substantial data loss and maybe inconsistencies in your data as well. Again, something you might not tolerate in a high performance system. So how does messaging come in and help? HTTP by nature is all about synchronous processing. It just cannot do async. So messaging comes in between the two servers that you're trying to communicate with each other, says that, hey, hold on, I don't need you to communicate directly from service A to service B. Let me come in. You put your request that you're sending to the service B into my little port that I have here, and let the service B, who is ready to take action upon the request, fetch that little request from the port of request and then act upon it. So that is the third person in between. So what happens is service A can continue to send requests into the port of containers, which is your message queue or message brokers, and service B can take that request and act upon it. So it is irrelevant whether service A and service B and up are running at the same time. All that matters is the request is stored durably in your message queue. And that's what exactly some of the tools and choices that I'm going to talk to you about today does. And when it comes to tools and choices, we have a variety of options. So this is a picture I'm really proud of because I took it at NDC Melbourne. And I love the look of this picture. Colorful lamingtons, nothing to beat it. But I don't have cakes on the menu today because what I have on the menu today is Azure Service Bus, Amazon SQS, and RabbitMQ. These are three of the most popular choices out there. Some of them are on the cloud, some of them on-prem. And at particular, we say that RabbitMQ and Azure Service Bus are our primarily used or most popular transports. Going ahead in my slides, you will have a lot of code. So that is all in a GitHub repo, which I will share as a part of my resources. And there's also a comparison kind of table that I've put together, which is again in my resources. So stay till the end. I'll share the resources at the end with you all, to my online audience as well. So how do we compare and learn about these message brokers? Because these message brokers ultimately have similar patterns and features underneath the hood. We'll talk about things like send, receive, publish, subscribe, dead letter queues, message ordering, and delivery guarantees, which are common features and patterns that we see across the message brokers. And in between these, while these patterns are similar, they still have things that you need to watch out for, which I will highlight throughout my talk. And we will also talk about standout features. AWS Simple Queue Service to begin with, because it's a simple and reliable, fully managed queue. There's no reason why I put it in the beginning. It's just that I start with one cloud service. It is a fully managed queue which requires minimal maintenance, but it is AWS only. So if you are an AWS house, then you might rely on SQS, or if you are just in need of a simple queuing system, this is again a great choice. And one of the key features of AWS SQS is that it can auto scale. So you can store nearly unlimited amount of messages in your queuing system. It auto scales on demand depending upon your throughput. And being a cloud offering, it has integrations with other AWS offerings like AWS Lambda and step functions, for example. There's a list of things that it can actually integrate with. These are some of them. With SQS, the message sizes can go up to 256 kilobytes. And if you have large message requirements that goes over and beyond 256 kilobytes, use AWS S3 buckets. Again, that is another integration. In this instance, what happens is it stores the actual message in the S3 bucket with a pointer to that S3 bucket in the SQS queue. So that's what happens. You can store unlimited amount of messages in the queue, as I said. And if you want to have batching of messages for sending or receiving or deleting, you can achieve that too. But the batch size is a maximum of 10 messages. And the total batch size cannot surpass 256 kilobytes. So there's an upper limit on the number of messages in the batch as well as the actual batch size. Being a cloud offering, it is not free. The first 1 million requests a month is free. And then you have to start paying for everything over and beyond that. You have to consider every SQS action as a request. So send, receive, delete. Even if you use the AWS console for receiving or polling for messages, that is also receiving. That costs money. And it puts things into perspective when you think that each 64 kilobyte chunk of payload is one request. So by that definition, 256 kilobyte of message is 4 different requests when it comes to, say, receive. We can talk about standard queues, which is one of the features of SQS. This is what most people out there use for their requirements, which gives you very high, nearly unlimited number of API calls. So nearly unlimited throughput is what you get by definition. You have durability and redundancies because you have copies of the message stored across multiple servers of AWS across different availability zones. So you have this concept called as distributed queues. You get best effort at ordered message delivery. SQS tries to deliver the messages as they are in the order within the system, but that cannot be promised always. So if you have ordered requirement needs, which is very, very rare, this is probably not the right choice. And SQS standard queue focuses on at least once delivery guarantee. So which means that your receiving end application of the consumer needs to be idempotent. So if a message is received more than twice, the work that it does behind the scenes needs to be an idempotent action. So let us talk about send and receive in SQS, which is the scenario in which service A sends a message drops it into the SQS queue, and then service B picks that message from the message queue and acts upon it. So sender and receiver. You can also have multiple instances of sender sending messages into the same queue. You can also have multiple receiver of the same kind trying to get message from the same queue. But at any given point, a specific message will only be handled by a specific consumer. So this is the competing consumers pattern. So all that is possible with SQS. So how does the code look like? We start off with creating an Amazon SQS client using an access key and a secret. And then using the SQS client, you can send the message using the send message async API. And I need to use the send message request object as shown in the example on line 17, passing it the queue URL as a property and the message body in this case, which is a serialized JSON object. So that is sending the message. And on the receiver side, again, we start off with the SQS client that I showed you. And I start off with receiving the message using a long polling operation or long-standing polling operation. The most important part while receiving a message is to make sure that once you've processed the message, it needs to be deleted explicitly by issuing the delete message async command. This is very important. Otherwise, the message goes back into the queue regardless of whether you have processed it or not completely, and then it gets redelivered. So this is the most important step here, and this needs to be done. You can also enhance the message that you are sending as a part of the sender by adding message attributes. So in this case, I have created a dictionary of string key value pairs and then attached it to the message and send that along with the message body as message attributes as seen in line 24. But on the receiving side, it gets a bit tricky. There's a little gotcha here. I lost 1 hour with this, so don't be Poornima. Watch out for this because you have to explicitly specify what message attributes you want to receive as a part of your receive operation. You say all, in which case you get all the message attributes, or you specify the specific attributes that you want to receive. And then you can use that in your processing. You can use that to say, have some routing adjustments or routing logic in place. But when you use these message attributes to build up your own routing logic, what you are building here is a version of mediator. Don't do that. Don't reinvent the wheel. Yeah. So stick to mediator and then use SQS. Fine. Another feature of SQS, this is a standout feature. This is long polling and short polling. Short polling is what we have on by default. So think about the distributed queue system that I spoke to you about. With short polling, which is the default, SQS, where it tries to retrieve the message and send it along to you, it only samples a subset of servers. So if you have 10 servers through which the messages are spread out, it goes and looks for messages in, say, 6 random out of the 10. You do not have control over which servers it samples. That is up to SQS. So which means that you get a responsive application, but you also get empty responses or false empty responses because the subset of servers that was sampled does not have any messages. But the 7th one, which might not have been sampled, has a message. That is possible. So which means that it might add to your cost, but you have a responsive application, which is what you might need. But if you can't tolerate that, you also have long polling, which queries all the servers and then responds with a message only when it has at least one message to come back to you with. So which means that you have a less responsive application, but you don't have false empty responses, and therefore it can help with reducing cost as well because it waits till there's at least one message for you to come back with. And all this can be set up at queue creation time, but you can also tweak it per receive message request. So in my example, if you look at line 2, when I'm forming the receive message request, I haven't specified the wait time seconds at all. So if I am not specifying that property, it means it is short polling. But in the second example on line 11, there is a wait time seconds set to 10. So if you have any non-zero value for wait time seconds, which is below 20, you have long polling. So again, that needs to be adjusted. 20 seconds is maximum that you can go up to. And Another feature is visibility timeout. So this is not a standard feature. This is kind of a repeatable pattern that you find in SQS, RabbitMQ, as well as Azure Service Bus under different names. But basically, it is a feature that protects a message against unhealthy receivers that cannot process message. So remember the competing consumer pattern where multiple receivers can look at the same message. So once a message has been delivered to a receiver, that message is hidden to the other consumers that are trying to consume the message. So the idea is that the message is hidden to other consumers while the message is getting processed, and the receiver needs to make sure that the message is processed as well as deleted off the SQS queue within this visibility timeout period. If the processing as well as deletion doesn't happen within this timeout period, the message goes back into the queue, becomes visible to other consumers, and gets redelivered. So that is visibility timeout. And again, this is something that can be set up at the queue level at the time of queue creation, but you can tweak it at the receive level as well by introducing the parameter called visibility timeout, which is set to 40 seconds in this case. The default is 30 seconds. The max is 12 hours. So if your receiver takes 10 hours to process the message, which is possible in certain scenarios, that can be done. And there might be legitimate cases where receiver is trying or finding it hard to process the message. So you can implement like a heartbeat mechanism to keep incrementing the visibility timeout period if needed using the change message visibility async API. But even then, if you keep extending, it can go only up to 12 hours. It cannot exceed the 12 hours. So this means that as a best practice, you need to adjust the visibility timeout based on the actual time you think it takes to process the message. So a little bit of trial and error is needed here. And be mindful, long visibility timeout means you can have delays and retries. So for example, if you set the visibility timeout to be 5 minutes, when it actually takes like 10 seconds to actually process your message, say 3 seconds into processing, the receiver crashes, it still waits that entire 5 minutes before the message becomes visible again and gets redelivered. So try and adjust it, have a little bit of buffer, but nothing too long. Definitely things can go sideways as well with distributed systems, and that's where dead letter queues come in, because ultimately we want all our messages to be durable, right? So that is where dead letter queues come in, and these are queues for holding messages that cannot be processed. And the only way that I know something can be dead lettered, at least at this point, is by exceeding what is known as maximum receive count. Every time a message is delivered to a receiver, not processed, just delivered, there is a header value called the receive count attached to the message, which keeps incrementing. So the maximum receive count is something that you can set up at the queue creation level. Say it can be 5 or 10. So if a message has been delivered more than this value, it dead letters. But happy days in SQS, because dead letter queues are not created by default, we have to make sure that they are created and configured. Another gotcha is that a receiver cannot dead letter a message explicitly. A receiver cannot say, I am too lazy, I do not want to process the message. That's not possible. So which means that every message has to go through the loop of receive, fail to process, go back, retry, keep on retrying till that maximum receive count is exceeded, and then dead letter. So that also probably can incur some cost, because sending, receiving, and deleting is all SQS actions that cost money. So adjust the visibility timeout as well as the maximum receive count when it comes to DLQs. So how can you configure DLQs in the AWS console? So you have to create a queue and say that is the dead letter queue for a source queue. In this example, I have set the queue that I've created to be the dead letter queue for my standard queue, which is what I have here. Move the mouse away. And then I have to go to my source queue and select the dead letter queue for the source queue and say what is the maximum receive count. So this is where I configure the maximum receive count. So maximum receive count actually only matters, or it comes into perspective only if you have a DL queue in place. And once this configuration is done, you can start having the redrives from the dead letter queue. So any messages that then hit the dead letter queue can be redriven to the source queue or a custom destination. So which means that when you start the redrive, the messages that are in the queue from the various senders and the messages that are redriven from the DL queue, they are all mixed up in the SQS, and then it'll be delivered. So again, we are looking at best effort at order delivery, but in most of the cases, you don't need order delivery at all. Another gotcha is that expired messages are permanently deleted, not DL queued. So they don't just sit in the SQS, they are just permanently deleted after the time to live is over or time to live is hit in a message queue in SQS. And if you have really that real need for ordered messaging, you can look at what is known as FIFO queues in SQS, which is again a 2-hour topic in itself. Things get really complex here because there are so many edge case scenarios that you need to think about. But FIFO queues helps with ordered message delivery. And the delivery guarantee, unlike the standard queues, is exactly once. So each message is delivered exactly once. But if you want true exactly once processing, this is not what you need to stick into. You need to bring in an integration pattern called the outbox pattern. With FIFO queues, retries do not disrupt the order. And there's baked in or built-in message deduplication using a deduplication ID, which you can specify as a part of your application, or bring in content-based deduplication. So regardless of how you do it, the message delivery order and the processing order is maintained with FIFO queues. So I'm only sharing this much on FIFO queues, but it is a topic that you can read about. It actually makes you think about a lot of edge case scenarios, which is what I did as well. We can talk about publish, subscribe. So what I'm doing right now is publishing my talk, and you are all listening to me, so that is subscribing to the talk. That is exactly what we have with publish, subscribe. With send, receive, the message is more of an instruction. Do this, do that. So we say that the message in send, receive or point-to-point communication is more of a command. With publish, subscribe, it is all about things that have happened. It is facts. And I'm just saying that I have done something. So it is an event that has happened, something that cannot be changed. It is a fact, and that is the basis of publish, subscribe. With SQS, there is no native pub sub. You have to bring in what is known as the AWS Simple Notification Service, or SNS. So when you bring in SNS, what you have is a producer service which publishes events into what is known as SNS topics. And the SNS topic acts like a fan out and pushes out those events into the SQS queues. You can bring in standard queues or FIFO queues. And from there on, everything that I spoke about, the visibility timeout, the long polling, short polling, receiving, all that comes in. So till about here is where SNS comes into play. After here, in these two rectangles about SQS queues and consumers, it is all about receiving a message, what we just discussed. Code-wise, we start off with the Amazon Simple Notification Service client, which is an SNS client. And using the SNS client, you can publish an event or publish a request into the SNS topic. So not the API, it is publish. And things doesn't stop here, because the next thing is you have to create a subscription. So for that, again, starting with the SNS client, you issue a subscribe async request. If you look at line 8, there is a topic ARN. That is the topic that the subscription is for. You also have to bring in what is known as an endpoint. As for SNS, SQS is an endpoint. That is the terminology. You can bring in, SNS can have additional endpoints like email, SMSs, all that is possible. But as far as SNS is concerned, SQS is an endpoint. And that endpoint needs to be created before you can subscribe. It does not create a virtual queue, for example, beneath the scene. It has to be an SQS queue that is subscribed to the SNS topic. But from there on, once you have created the subscription, it is business as usual with receiving the message, processing it, and deleting it. So this is all about fan out, where every subscription gets a copy of the event that is published into SNS topic. But if you want to have a subset of messages delivered to your subscription, you can do that as a part of your subscribe request using what is known as filter policies. So here I have created a filter policy, which is a very basic JSON, which says my attribute int and value 5. And in my subscribe request, I have defined filter policy of the filter policy that I've just created, setting the filter policy scope to message attributes. So in this instance, only messages that has an attribute called my attribute int, which matches a value of 5 in the message attributes of the message, gets into the SQS queue. The message the filter policy scope of the subscription itself can be message body, in which it goes and looks for the message attributes in the message body. But in this case, we are sticking to message attributes. Another gotcha that you might want to look out for is raw message delivery with SNS topic. If this is not turned on, what happens is your message is buried deep inside the SNS payload itself. So it is wrapped inside the SNS payload. So another gotcha to watch out for. The biggest gotcha of it all is to make sure that SNS actually has permissions to publish to the SQS queue. So just a subscription wouldn't help. You also need to make sure that the SNS topic or the SNS service has the permissions to publish to the SQS queue that is subscribed. So a lot of manual configuration is needed. You can also have SNS dead lettering into the dead letter queue of the queue that you've just created. But again, that means you need to make sure that SNS has permissions to publish to that DL queue. Again, topics gets confusing and more complex here, something you might want to play around with and see how it goes. And that brings me to Azure Service Bus, which is my favorite service out of the three today, because it says it does what it says on the tin. And unlike SQS, which is a queue, this is an enterprise message broker, which brings in things like routing, message transformation, for example, more features. It's more than a queuing system. It has native PubSub, for example, so a little bit more advanced than, or a lot more advanced than a message queue. It is again a PaaS offering in Azure. And being an Azure offering, it means that there are integrations with other Azure services like Event Grid, Logic Apps, Azure Functions, which is my favorite one again, because you can have triggers which trigger Azure Functions when it receives a message from Azure Service Bus. You have some local development experience as well with Azure Service Bus these days, because you have the Azure Service Bus emulator. And you have Service Bus Explorer if you want to administer the message entities outside Azure portal as well. Of course, it costs money. There's a standard tier which is recommended for development usage, which costs about $10 for 13 million operations a month. But underneath the hood, it uses a shared capacity for message persistence. On the premium tier, which is used for production or recommended for production workload, it uses dedicated capacity beneath the hood. And I heard somewhere, I think probably in Clemens Foster's talks, that with standard tier, what it uses for persistence of message is SQL Azure, but with premium tier, it is totally something different. We can talk about send receive. What I want to highlight here as a part of send receive is the two different modes that Azure Service Bus can operate in. The first one is a destructive read. If you want really high throughput applications where you can tolerate message loss, because in this mode, messages are marked as consumed and then sent to the receiver. So while processing or while the message is being just delivered to the receiver crashes, the message is gone. There is no way to retrieve it. This focuses on at most once delivery guarantee. So it is the weakest of the delivery guarantees, if you ask me. Most of the brokers out there goes for at least once delivery. So that is destructive read for you. And the second one, or the recommended one, is the peak lock mode, which is the non-destructive read, where the message is locked and then sent to the consumer. So which means that something like the visibility timeout period should be in action here, and that is peak lock timeout for you. So the idea is that message is processed and a complete command issued within the peak lock timeout, and the message gets taken off the queue. With peak lock mode, we focus on at least once delivery guarantee. Looking at the code about sending, you create a service bus sender. And then using the sender, you can use the send message async to send your message, which is an object of type service bus message. So notice the API, we are in the send mode here. And on the receiver side, you create a service bus processor. And on the processor are event handlers, which you can implement. There's event handler for processing a message as well as processing error messages. And that is my implementation of the process message async. The event handler for that, where I process the incoming message and then issue the complete message async command, as in line 29, within the peak lock timeout period to take the message off the queue. Otherwise, again, it goes back into the queue, gets unlocked, and then gets redelivered. You can have metadata added to the message, and metadata in Azure Service Bus world is called as application properties, which is very simple key value pairs. Things are very simple. You just send it along the message, and on the receiving side, you can just use it. There is no need to specifically ask for application properties. However, I think that there is an upper limit on the size of the application properties, which is probably like 64 kilobytes or something. With Azure Service Bus, the message sizes are 256 kilobyte in the standard tier and 100 MB in the premium tier. The queue itself can only be up to 5 gigabyte in Azure Service Bus. There are ways to extend it. Let me come back to you in a later slide about that. You can also batch messages. The batch size should be 256 kilobyte maximum, but there is no upper limit on the number of messages. In the premium tier, batches can be up to 1 megabyte. So remember I told you about extending the size of the queue? Partitioning is what can help it. So you can take the queue size up to 80 gigabyte if you introduce partitioning. But it does come with a cost, because each partitioned queue or topic counts towards a quota of 10,000 entities per namespace. So it does have an impact on the cost, but it gives you better resilience and better throughput and availability, because it's something like the distributed queues underneath the hood. There's native publish subscribe with Azure Service Bus, where a sender can publish to the topic, and then subscriptions can be created, and receivers at the end of the subscriptions keep receiving the message. But the biggest difference here is that these subscriptions that you see as subscription A, B, and C, these are like virtual queues which you do not need to create. You create the subscription, and underneath the hood, it creates the virtual queues for you, and then it goes and subscribes. All you need to make sure is that there's the receiver which can create the subscription to the topic. You can have a maximum of 2,000 subscriptions per topic in Azure Service Bus. And if you want larger fanouts, you can implement auto forwarding by configuring second level or even a third level or a fourth level topic. But after 4 levels, things starts to DLQ, so beware of that. So we again have fan out and filtered message scenarios here. So by default, every subscription gets every message, a copy of the message, but you can bring in a subset of messages alone to the subscription by using what is known as subscription rules. So you can have filters in each subscription rule to filter out select messages, and you can have actions to enhance the message or annotate the message as well. So that is a standout feature of Azure Service Bus, message transformation. But each subscription can have multiple rules if needed. And the filters itself, they are nothing like the filter policies that we saw in SQS. It's more elaborate because you can have SQL filters, which use a SQL-like expression evaluated against the system and user-defined properties. You can have Boolean filters, which filters all the subscriptions, or it doesn't take any subscription using the false filter. So the true filter is what we have on by default, which is for the fan-out scenario. And you can have correlation filters, which is a set of conditions, again, matched against user and system-defined properties. It uses a case-sensitive string comparison. But note that, unlike SQS, where you can compare on message body itself, this is all on message attributes or the application properties or the system-defined properties, nothing else. So as I said, jumping the gun here, filters cannot evaluate message body. So if I want to show you an example of how everything is, I have a publisher that publishes to a topic. I have 3 subscriptions created. The first one uses a Boolean filter, a true filter with no action. The second one, I am having a SQL filter, which filters out or makes sure that only messages with an application property of color red is chosen into the subscription. In the third subscription, I'm using a correlation filter where I select messages with the subject blue and then add an action to enhance the message by adding a property called action set is equal to yup. So let us see the code in action. From a sending perspective, I create the service bus sender, and I, as a part of the service bus message itself, I set the subject to be a random chosen color out of the colors array. The subject is like an application specific purpose of the message. Sorry, some water. I am also adding the color as an application property. That's because I want to show you that you can have filtering based on the subject or filtering based on the application property. And then I'm sending the message. So I am publishing an event, but note the API, it is send. With SQS and SNS, it was send and publish. Here, everything is send. And on the receiving side, if you look at the first piece of code here, I hope you can see the code which is clear. Otherwise, go to the GitHub repo. Everything is in there for you. You start off with the SQS, not SQS client. There's some code I have omitted for the sake of the screenshot. I create a subscription first using a topic name and a subscriber name. That subscriber name matters, that needs to be unique. And then I attach the rule of the true filter. So note that there is no queues coming in here. It's only the subscriber name and a topic. And in the second example, again creating a subscription, and then I'm attaching a SQL rule which says that filter out all the messages or get me all the messages which has the application property color set to red. In the third example, I'm using a correlation filter after the subscription has been created, suggesting that all messages with the subject blue should be selected in. And not only that, I also need to have a new property called action set equals yup set on the message. So that is how you create a subscription and subscribe, and you can have subscription rules and filters added to the subscription. So as a best practice, use correlation filters over SQL filters because it is more efficient in processing and have lesser impact on throughput. You also can have dead letter queues in Azure Service Bus, but thank God, because dead letter queues are created automatically, you do not need to manage them separately. And dead letter queues can be accessed at QURL/$deadletterqueue. And what are the scenarios in which dead letter queues or a message can dead letter? When it exceeds the max delivery count, which is like a parallel scenario to the max receive count in SQS. When the number of retries have exceeded the max delivery count, the message goes into DLQ. Message can expire and then get into DLQ, so there's more resilience and more sturdiness with your messages here, because you can configure Azure Service Bus to dead letter queue your expired messages. If you have errors in processing subscription rules, then messages can dead letter. When a message does more than 4 hops in auto forwarding scenario, so if you chain topics, if you hit more than 4 hops across topics, then a message dead letters. That's the maximum. You cannot configure that anyhow. The most importantly, you can have application level dead lettering as well. The application itself can say, I do not want to process this message. That is possible as well. So which means that you do save upon some processing that way. If you want message ordering, then you can rely upon message sessions, which has a slight overlap with the FIFO queues in SQS. Because message sessions is all about grouping related message into what is known as a session and then sending it. So you can have, say, multiple sessions with related message, each message having a unique session ID, which is common to those set of messages. And when a receiver receives the first message of a session, that session is completely locked to that receiver. It is only that receiver that can then process the messages in that session from then on. You can have the receiver processing multiple sessions concurrently, but then all those sessions are locked to that particular receiver. You can release the lock as well when the receiver methods close or the lock expires. And you have guaranteed message order within a session, and retries does not disrupt order. So deduplication is another feature in Azure Service Bus that is, but with FIFO queues that was baked into FIFO queues. Here it is all about grouping messages together into a related session and then getting those messages in an order. That is the use case here. If you want to send message and use message sessions, you have to first create a session ID. In this case, I'm using a very simple random out of 3, and then attach that session ID to your service bus message. When you have message sessions, you also need to denote as a part of your application which is your last message, so that at the receiving end, the receiver can make use of that to then release the session. So in this case, I am denoting that this is one of the messages that I'm sending is the last message of the session using an application property called isLast, and then sending the message. So in this case, if the count of I is 99, that is the last message in the session. On the receiving side, it is business as usual. You just start handling or start with the event, the handler for the process message event. I am using that isLast application property to check whether this is the last message of the session and then release the session if needed. Of course, you need to complete the message as well. Otherwise, it goes back into the queue and then gets retried. So the use case for message sessions would be for related messages, group them together. And as a best practice, always have a unique session ID for that group of messages and let it be generated by the application itself. And the maximum number of sessions that can be processed concurrently by any receiver is 8. So it does have some impact on the throughput as well. Another standout feature of Azure Service Bus is the transactionality, because with the transactional broker like Azure Service Bus, you can group 2 or more operations into a single execution scope, which means that I might be doing some processing and then sending 2 messages into a message queue. With transactionality, it ensures that all those 2 send operations succeed or fail jointly. There won't be a scenario where one message gets sent, and between the first message getting sent and the second message getting sent, if something happens, there's no scenario where one can succeed and one can fail. Both succeeds or both fails jointly. So ensures atomic operations. And the operations that can be a part of the transaction scope is send, complete, abandon, dead letter, defer, or renew lock. Receive is not a part of this operations list because it is assumed that receive is always under peak lock. So that is transactional by default. What happens after processing? From the point of processing to completion, what happens can be put in a transaction scope. To explain this further, I have some code here. So in line 5 and line 11, where I've highlighted with arrows, I'm trying to send a message. And then I'm trying to get the number of messages after each send message operation. You can see that without transactions in place, every time a send message operation is done, it increases the number of messages in the queue. However, with transaction enabled, as in line 1, using transaction scope, if I try to send a message in line 4 and line 10, same code as usual, and try to get the number of messages within, you can see in the code output that the number of messages in the queue is 0. But when the transaction is complete, and then I try to get the number of messages from the queue again, that is when both the send message async operation actually commits into the queue. So that is transactionality for you, but this is all happening within the same queue. 2 send operations to the same queue. But you can also have operations like this in a transaction where you complete the message and then send two different messages to two different queues. That also can be a part of transaction, that is cross-entity transactions. That is also possible. So here is the code example for that. You have a transaction scope which wraps up a complete message and then also sends messages into two different queues. But a gotcha here is that your business data is not taken care of or is not a part of the transaction processing at all. For that, you need to bring in outbox pattern. So that is another integration pattern which gives you true exactly once processing. That brings me to RabbitMQ, which is the open source message broker with commercial offerings available. It is quite a vast topic in itself, and it supports multiple protocols like AMQP, MQTT, and STOMP. Again, it offers at least once delivery guarantee because that's primarily the standard that we see out there. And it has active community support. And we recommend clustering to support high availability and distributed load. It is deployable on premises or in the cloud. And it is compatible with containerized environments with Docker, like Docker. So if you want a local development experience with RabbitMQ, a Dockerized instance is what I would suggest, or what we recommend and what even I use for development as well. But all of this shouts out loud that RabbitMQ management is a skill set that the team needs to have if you are trying to bring in RabbitMQ, which is a totally vast topic in itself. So this calls for a lot more learning curve with RabbitMQ. With RabbitMQ, the queue size is limited by your server disk capacity, and you can have arbitrary message sizes going up to 512 MB, but please don't do that. Use the data bus or the claim check pattern. You can also have message headers dictionary as a part of messages. Talking about send and receive, there are two things again that I want to highlight here because it's very different from the modes in Azure Service Bus or in SQS, because this also takes into consideration the competing consumers. So there are two modes in which competing consumers can work. The first one is round robin, where messages are delivered to the next consumer in sequence. So the load of the consumer itself is not taken into consideration. But with fair dispatch, as it says on the tin, it makes sure that the load of the consumer is taken into account while delivering the message. So it looks out for which receiver out of the competing consumers has the least unacknowledged messages, and that receiver gets more messages so that whoever is keeping busy can continue and is not overloaded, and messages are not waiting in queue to be processed. So we start off with a queue declare async. I wanted to highlight the durable equals true parameter here, because with RabbitMQ, you can have queues which do not persist. For example, if you have very high throughput scenario, this is what usually is seen used out there. But in all honesty, you want durability for your messages. So consider using durable queues as possible. But just having a durable queue wouldn't mean anything, because unless and until you have the persistent property added to the message, it is not a persistent message itself. So when you have durable queues, the queue itself can survive a broker restart, but the messages will not. If you want persistent messages, it should have the persistent true basic properties added. And then using the basic publish async, I can always publish a message. So with Azure Service Bus, send and publish was all sending. Here, sending is also publish is also published, not the API differences again. And on the receiver side, again, you have callback based event handlers. So the received async callback is what I would implement. I wanted to highlight the channel basic async here, where it uses the concept of delivery tag to go and say that, yeah, I have acknowledged that the message has been completed, complete processing, you can now go and delete it. I also wanted to highlight the auto ACK equals false. So this is where the receive and delete and the pcloak mode of Azure Service Bus comes in. Auto ACK set to false means you have to explicitly say that I have completed the processing. Auto act set to true means the minute the message is received, it auto acts saying, yeah, message received, you can delete it. So that is more like a destructive read operation. To see the round robin in action, if you look at the screen here, I have one publisher that is keeping on sending messages. But if you look at the two receivers, the messages are in sequence. It goes 1, 2, 3, 4 between the two receivers. That is round robin for you, where messages are delivered in sequence. With the fair dispatch, the only change that you need to make is add this line of code, basic was async with the prefetch count set to 1. And the way I'm introducing the delay to show the very busy receiver is, in my message, there is a number, and based on the number, I am introducing a task.delay. So for number 1, it would be 1,000 millisecond delay. For 5, it would be a 5,000 millisecond delay. And with this fair dispatch mechanism in place, if you look at the screen here, you can see that despite the number of receivers, it is always the receiver which is less busy that gets the message. So it is not a sequential delivery. It goes 1, 2, 3. Then it is the second receiver that has received 4 and 6. It is the right receiver that has received 5 and 8 and 10 and 13. So it's not a sequence. It is based on how busy the receiver itself is. You also have publish, subscribe in RabbitMQ, and this is where we need to talk about exchanges and bindings. Because with RabbitMQ, messages are always sent to an exchange, never published into a queue directly. So what are exchanges? Exchanges is your routing table. At the point of creation, they are empty. So if you are wondering how messages were sent into the queue and then received, I was not sending it to the queue. What happens beneath the scenes is, if I do not specify the exchange, then it uses the default built-in RabbitMQ exchange beneath the scenes. So that exchange is your routing table, or any exchange is your routing table, for example. And what you have is bindings. Bindings define the routing rules. They are effectively the relationship between an exchange and a queue. And the routing logic itself is implemented by using a specific type of exchange with the routing keys. So you can have direct, topic, header, or fan-out based routing logic based on the different type of exchanges that you use. With fan-out exchanges, this is like the broadcast scenario where a copy of the message is received by every queue, or every queue bound to the exchange. So which means that every receiver receives a copy of the message. So here the main things to highlight is that when I declare exchange, I define or specify a name for the exchange, which is logs in this case, and the type of the exchange, which is the fan out exchange. And then I can publish to the exchange. Note that there is nothing called the routing key, which is specified here. And the routing is based on the routing key, but here the routing key is completely ignored. So note that again, I'm using the publish. So sending is publish, publishing is also publish in RabbitMQ. On the receiver side, how does the binding and everything work? So all I need to do is, when I declare the subscriber, I don't need to create a queue. I need to create a queue, but in here, it is a system-defined queue name that I'm bringing in, because subscriptions are seen as transient by RabbitMQ. If it is restart and lost, it's fine, but that is how things work in RabbitMQ. And I am connecting this receiver to the exchange that I just created, which is logs. And again, the routing key is set to empty. From there on, the receiving process is same as what I explained. You have the callback, which I have implemented, and then I can consume and act the message to say that everything is completed. With direct exchange, this is where you can specify a routing key to filter the messages that a subscriber or a receiver receives. So here you have producers publishing into what is a direct exchange, and then you bring in routing keys. The routing keys are specified as a part of publishing a message, and on the queue side, you specify which routing key am I looking for. So then it filters out all the messages that are of that particular routing key and only pulls in those messages. And the consumer can act on them. So here the most important thing is when I declare the exchange, I have an exchange type of direct, and then I specify a routing key as a part of my message publishing. Here the routing key is something that I've randomly chosen from the routing key array, which is info, warning, or error. And that routing key goes with the part of basic publish, the publish mechanism itself. So it is not actually related to the application property or attributes. It is with the publish mechanism itself. And on the receiving side, again, I have to bind to the exchange that I created, that is of exchange type direct, and I can specify the routing key here. So here I am declaring a queue and then binding it to the exchange that I created, specifying the routing key. So in this case, I'm using two different subscriptions, two different bindings. So all messages with routing key info or warning will be selected in. There are two different other exchanges as well, which is topic exchange, where you can have pattern matching in your routing key if you want more complex routing key patterns, because with direct exchange, it is always a single word. With the headers exchange, you can then rely on the message headers for filtering properties. So that is all about the exchanges. You can also have dead letter exchanges. And again, when you have delivery limit exceeding, you can have messages dead lettering. When a message expires, it can dead letter. When a consumer rejects the message, it can dead letter. Messages can get dropped when the queue length is exceeded, because remember, you are limited by the queue disk size. So there's application level dead lettering as well. Another standout feature is, again, transactions and reliable publishing. RabbitMQ can be a transactional broker which supports atomic transactions, but it is less performant. So use it only when you have really, really high consistency needs for critical operations. You also have a lesser ACK-based consistency that can be provided as a part of publisher confirms. You can use this for high throughput apps. That is what is recommended by RabbitMQ. This is more performant than the transactions as well. A standout feature of RabbitMQ is priority queues, where you can prioritize certain messages over the other. So when you create queues, you can define a X max priority on the queue, which sets it up as a priority queue. And from there on, you can assign a priority value to each of the messages that you send. And if it has a priority value, such messages will be prioritized in delivery over the other messages which does not have a priority. But priority queues are resource intensive, so use it only when needed. And there's also something that I want to mention about the queue types itself in RabbitMQ, because it uses different type of infrastructure beneath the hood. With classic queues, it has optional replication and persistence, no order guarantee, but it offers very high throughput. But what we recommend is the quorum queues, which is based on the built-in replication using the Raft consensus algorithm. It is always persistent, uses FIFO ordering guarantees, highly durable, but lower throughput compared to the classic queues. Another feature of RabbitMQ is that it relies on the public plugins architecture to extend RabbitMQ itself. For example, if you want to bring in delayed delivery, you need to have a plugin in place. So again, there is the need for skilling up and learning all about RabbitMQ management in this instance. But if I have to show you something about RabbitMQ plugin, this is the web management plugin, where you can go and have a look at the exchanges and the queues and the throughput and see what is going on beneath the hood. So this is something that you can have locally installed as a part of your developer experience as well. So you have learned all of this. I've been talking to you all about message queues and brokers. What are some of the questions that you can ask yourself to get started on what should be the message queue or the broker that you should be using? Are you targeting the cloud? If yes, then what is your preferred cloud provider? Is it Azure, in which case go for Azure Service Bus? If it is SQS, go for if it is AWS, go for SQS. And if you're not targeting the cloud, RabbitMQ might be a good option for you. Now, I have spoken only about these three. There are others like IBM Zero MQ, Active MQ. So you need to bring all of that into the picture as well while you're asking on this particular question that I've specified here. But there are other things to consider as well. Like, what patterns do you need to support? Do you need send receive, or are you going event driven with publish subscribe? What is the average message size? What is the message order delivery like? What is the delivery guarantee? What about transactionality? What about the message throughput? And what is your team's expertise with the technology? How important is monitoring and observability? And what is the local development experience like? So all these are countless questions that you can ask yourself. And if you've done your research quickly and fairly and consistently, you will know that this is just the tip of the iceberg, because whatever I've covered today is all about that entry point into building distributed systems and maintaining them. Because what you will see that you need things like message routing, workflow, transactions, claim check patterns, serialization, and much more as a part of building and maintaining that distributed system that we have been talking about. 2, verifying all the edge cases, because I've been highlighting them throughout my talk, right? All in all, you will be thinking about implementing these 34 different patterns as a part of your project. So what is the output? Should you be building them, or should you be relying on something else? That is where messaging middlewares come in. So if I have to give you one important takeaway as a part of this talk, please use a messaging middleware, because whatever you build would be a cheap version of, not cheap in the sense, it might be quick and easy for you now, but in the long term, it is going to cost you a lot of money building and maintaining these 34 integration patterns. There are so many options out there. Service Bus, Mass Transit, Brighter, Rebus, Wolverine. Please use one of these messaging middlewares if you are to building a distributed system. Because think about owning a car. You wouldn't be building a car, right? You would be buying a car and using the amenities. Similarly, focus on the amenities and focus on what is bringing you the business value, rather than recreating those 34 integration patterns and then maintaining that yourself, documenting it and keeping it running. So don't reinvent the wheel. That is one of my final messages for you. Thank you once again for having me as a speaker and being my audience. And that is all my resources for the day. That is the QR code. And if you can share the resources to the online audience, that would be great. If not, I'll put it on LinkedIn as well as the YouTube video when it is ready. There's also the GitHub repo and the comparison chart that I spoke to you about earlier in this resource. So feel free to have a look. And of course, if you have any session feedback for me today, please do let me know. And of course, speakers can grow only if we have feedback. So, and also earn SSW points. So that is it from me. Thank you.